I want to talk about a very well-known topic in Calculus 1. It is the exact definition of a limit, of a finite limit, two-sided. It's sort of infamous in calculus lore for first-time calculus students. So what it's called is, well, first of all, it's going to be a very technical way to describe what limits are, whereas we've been looking at intuitive ideas behind limits. But what do limits mean exactly? So we're going to look at what's called the Epsilon-Delta, definition of a limit, okay? The Epsilon-Delta definition of a limit. So here we go. We say that the limit as x approaches a of some function f of x equals L if, and now we'll state the definition. And I'm going to kind of walk you through an illustration of what it means and talk about notation and things like that, okay? So we say that the limit as x approaches some finite number a of f of x equals some finite number L if. So if given any positive tiny number epsilon, so given any epsilon greater than 0, has to be positive. And when we say any, what it really means is you can make it as small as you want. So given any epsilon greater than 0, there is, meaning we can find, there is a delta greater than 0. Again, another small positive number. So given any epsilon greater than 0, we can find, or there is a delta greater than 0, such that when x, so x is approaching a, right? So such that when any x value is within delta of a. So remember, delta is a tiny number. It's always associated with x and with a in this particular format. So all this is saying, since delta is a really tiny positive number, x is really close to a. And that's what we mean when we say x approaches a, right? So when x is within delta of a, f of x, the y value, well, what's f of x getting close to here? What's it approaching, right? F of x is approaching L as x approaches a. So f of x is within epsilon, the other tiny number, of L. Okay, so that's what we're going to focus on. Let me show you a diagram of what this represents. It's going to be sort of a generic picture. So let's look at the first quadrant, let's say. And x is approaching a, so let's put a on the x-axis. It's an x value. F of x is approaching L, so L is a y value. So maybe let's put it right here. Okay, so we have a and we have L. And as x approaches a from both sides, the function should approach L. So this function may not be defined at a, right? We don't have to have a point at a comma L for this limit to exist. So let's assume the worst case and that it's not defined there. And then maybe the function does this over here and it does this over here, okay? So we've got some function. This is f of x. And we can see the behavior of the function as x approaches a. We can see that the limit is going to L, all right? So let's analyze this definition. So what it says is you are welcome to pick any tiny number epsilon you want. It doesn't matter what you choose, okay? And epsilon is a distance from L. So what we have here is, and I'm going to make it kind of big just so we can draw things out and you can understand it. So let's say epsilon let's say epsilon is the distance from L up to this point and from L down to this point. In other words, this y value is L minus epsilon, and this y value is L plus epsilon. So your epsilon above or epsilon below L, okay? So you can choose epsilon to be as small as you want. In other words, you're trying to get close to that value L, that limit value, okay? So you'd get to pick that epsilon. And so what the definition says is if the limit actually equals L, then if you give me that epsilon, then I should be able to determine a delta that surrounds A. So in other words, let me move to this side, delta that surrounds A. So let me show you a delta that would work. So delta is this distance from A to each of these red points on the x-axis. So this x value would be A plus delta, and this x value would be A minus delta, if you go delta to the right or delta to the left, okay? So the definition says when x is within delta of A, so if I pick any x value in this region within delta of A, so you can imagine if you sort of project that up here to the function, I'm sure my lines aren't straight here, but you get the idea hopefully. You can see that the corresponding y values, the f of x values, for all the x values that live in here are in this band coming over here to the y-axis. So any x value that lives in here comes up here and turns into a y value that lives there. Those are f of x values. So if we control the x values, if we squeeze them in close enough to A, we can get the corresponding y values to be as close as we want to L. Remember, epsilon is arbitrary. You could choose any small epsilon you want. And if the limit is in fact L, then I should be able to, or anybody should be able to find a delta so that all of the x values that live within that delta radius have an image of y values that live within this epsilon radius of L. Okay? So it's a really, really neat concept. It's kind of fun to use the notation and the Greek letters to describe this, and it's interesting to play around with. Now, that's the definition, and this is a visualization. There can be numerous deltas, right? I chose a delta small enough so that the y values are here, but you can see that I have some space left inside my epsilon radius of L. So I could always, if I wanted, I could expand my delta further so that I get as many y values in there as I can. But you don't have to do that necessarily. So that's an introduction to this definition. Now, typically, when it comes to the mathematics behind this, when you do things with this mathematically rather than just visualize and understand, typically you're going to describe the x statement and the f of x statement slightly differently, okay? So rather than saying x is within delta of A, I'm going to cross that out. Nothing's wrong with that necessarily. But mathematically what that's saying is the distance between x and A. In other words, x minus A. The distance between x and A means absolute value. So x minus A is how far apart they are, and absolute value ensures that it's positive. So this represents the distance between x and A. That distance between any x value here and this A value better be less than delta, okay? So instead of saying x is within delta of A, we would instead say that the absolute value of x minus A is less than delta. And that gives us something solid to work with mathematically. All right. Now, one little interesting fact about this is we also want to include that this absolute value is greater than 0. If x minus A equaled 0, then x would equal A. We don't care about when x equals A, we just care about when x gets close to A, right? So this ensures that x does not have to equal A. In fact, if x equals A, sometimes this falls apart. Okay, so I won't really get into that. I don't want to make this more complicated than it already is, right? Okay, so we change this x's within statement to an absolute value statement. We can do the same thing for the f of x statement. So instead of saying f of x is within epsilon of L, we're going to instead say that the distance between f of x and L, right, this tells you how far apart they are. To make it a distance, we need to put absolute values on it to ensure it's positive. So this is the distance between f of x, any y value here, and L. That distance better be less than epsilon. Okay? So now the definition says the limit as x approaches a of f of x equals L if, given any epsilon greater than 0, there is a delta greater than 0, such that when the absolute value of x minus a is between 0 and delta, the absolute value of f of x minus L is less than epsilon. Personally, when I read this, I still read this as, well, you could say the distance between x and a is between 0 and delta, and the distance between f of x and L is less than epsilon. That might help you relate the notation back to the actual definition and its meaning. All right, so that's an introduction to the epsilon-delta definition of a limit. It's not easy. Pause and rewind, work through the diagram yourself. Make sure you understand this. It's really important.